Welcome to Chapter 3, Describing Data Using Numerical Measures. In this video, we're going to talk about measures of center and location and interpret what these values mean, and construct and interpret a Box-and-Whisker plot. So we've got lots and lots of numerical measures that we're going to cover in this chapter. In this video, we're going to focus on center and location. Measures of center. By center, we mean where on the number line is the middle of the data. We have four ways of measuring that: the mean, median, mode, and if appropriate, the weighted mean. Other measures of location in the data are percentiles and quartiles. And by location, we mean where does the data, or a specific point in the data, lie on the number line. All six of these things are actually measures of location in the data. So we'll talk about first the mean, median, and mode. Those are the three primary ways that we measure center. In some cases, it's appropriate to use a weighted mean to measure center. So mean, or arithmetic average. This is the most common measure of central tendency. You guys remember doing this. You'd add up all the numbers that you needed to add up, and you divide by the number of numbers that you put in. So I've defined the mean here as the sum of the values divided by the number of values. So let's start by looking at the number line on the left here. We have 5 data points. Each blue dot represents a data point. We have a data point at 1, 2, 3, 4, and 5. If we add them up, we get 15. There are 5 values, so we divide by 5. The mean of that first set of data is 3. Notice on the right, I just changed the one data point from 5 to 10. So you might consider 10 an outlier. It's a value that's way far away from the other values in the data set. When I add up 1, 2, 3, 4, and 10, I get 20. Divide that by 5, and I get 4. The mean has been affected by this outlier. Now you might look at that and go, yeah, but 4 is not that much different than 3. But think about that. 4 is 33% bigger than 3. There's some notation given in the book that you should understand. We've got the Greek letter mu and the Roman letter x. If you notice, population is associated with Greek letters. That will help you remember that this Greek letter is a parameter. The sample is always associated with a Roman letter, so if you see the x bar, you know that number is associated with a sample. Now, some of you have seen the summation notation before, and some of you haven't. This big fancy E is a sigma. All it means is add up all the data points. The little I means each one of those individual data points. I is an index in the data. 1 to n. 1, start with the first row. N all the way down until we get to the end of the population. N is always the population size. So this really just means to do sort of what we did on the last page. Add up each of the individual data points, if we have all the values in the population, and divide by the number of items in the population. If we only have a sample, then all we can do is add up all the data points in the sample and divide by little n, because there's little n items in the sample. The median is the number that stands in the middle. So if you were to sort the data from lowest to highest, the median is the number standing in the middle. Half of the data would be above the median, and half of the data would be below the median. The only notation we really have for median is capital M with a little subscript D to stand for median. One of the good things about the median, and why we often report it even alongside the median is not affected by outliers like we saw a moment ago. So we've got the same data sets repeated here: 1, 2, 3, 4, and 5. 3 is the value that stands exactly in the middle. It's our median. Here we have that 1, 2, 3, 4, and 10 again. 3 is still the number standing in the middle, so 3 is still our median. The median is not affected by the outlier. To find the median, we want to sort the data from low to high. That's actually called a data array when you've sorted the data from low to high. Now we're going to start by finding the median index point. All that is a fancy way of saying which indexed value or which row in this sorted data are we going to get. We take our sample size and we really just divide it by 2 or multiply it by 1/2. It means the same thing. That's going to give us a position in the data. Now, if n is odd, I, that little index that we calculate, is not going to be an integer. We should then round up to the next highest integer. So if we had 6.5, we'd round up to 7, and we would grab the data point in the 7th position. If I is an integer, it means we have an even number of data points. We are going to take the average of the values in the ith and the ith plus 1 position. So if our median index point came up to be 6, we'd find the data points in the 6th and 7th position, and we would average them together. So here's an example. We've got the data sorted already from low to high. Note that there are 13 data points here. So when I plug 13 into my median index point formula, I get 6.5. 6.5 is not an integer, so I round up to 7. I'm going to go down the data till I find the 7th value. 1, 2, 3, 4, 5, 6, 7. Notice that 12 sits in the 7th position, so 12 is the median. One of the things that the mean and the median can allow us to do is begin to understand the shape of the data. Data sets can be symmetric. What that means is that the values are spread evenly about the mean. So you notice graph C in the figure below. The mean equals the median. What we notice is that the data look like a mirror image to the left and right of the mean. If the data are skewed, it means that they're not symmetric. In data that are not symmetric, the mean and median will not be equal to each other. So if you notice the graph A, we see the mean is greater than the median. This data is right skewed. Notice the longer right tail. Right skewed has a long right tail. I often call this the Bill Gates effect. So if we're looking at the income distribution for the United States, we have a median value that's significantly lower than the mean. I call this the Bill Gates effect because Bill Gates and a few other people that have a lot of money would be up here in this upper tail. They have a lot of money. They're way far away from most of the rest of us in this distribution. Because they make so much money, they drag the mean up above the median, making the data right skewed. In a similar way, the mean is well below the median in left skewed data. We have a few data values here that are very, very low, and they're pulling the mean down below the median. A long left tail indicates a left skewed distribution. Now, a data set does not have to be bell-shaped or something like a bell-shaped curve to talk about symmetry. I'm just using the bell curve here as an example. Another measure of center in the data, also a measure of location, is the mode. And you probably remember hearing about the mode before. That's the value that occurs the most often. It's also not affected by outliers like our mean is. We can actually use this for numerical or categorical data. It's possible for there to be no mode or even to be several modes. So I've given another data set down here. Remember, each blue dot represents a data point. So we have one value at 1, one value at 3, 3 values at 5, and so on. You notice that 5 occurs most often, so it's our mode. In the example on the right, there's no repetition. Each value only occurs once, so there's no mode here. Now you might be looking for a business example here of mode. So I'll use an example of when I took my daughter shopping when she was in high school. We would often go into American Eagle to buy clothes, as many of you probably do or have in the past. When she's in the dressing room trying clothes on, I'm standing at the clearance rack just outside the dressing rooms looking at what kind of bargains I can snag up. And as I'm scanning the rack, it quickly becomes a business problem in my head. I notice that there are about 75,000 pairs, okay, I'm exaggerating, about 75 pairs of size 0 jeans, and only 2 or 3 pairs of size 6 or size 8 or size 10 jeans on the rack. I quickly begin to think that the buyers for American Eagle may not understand what their typical sized customer is, or what the mode size of their customer is. Now, if we're trying to figure out which measure of center is the best to use for the data, there are actually different reasons why each might be the best thing to use. We always seem to see the mean of the data reported. It's the most commonly used measure, as I mentioned before. We know, though, if there are extreme values in the data, that that's going to cause a problem with our mean. So you'll often see the mean and median reported together, or the median just reported when there's extreme values. Mode is good when we're trying to look for the value that occurs most often. Now, I mentioned that you may also use the weighted mean. The weighted mean is typically used when values are grouped by frequency or relative importance. So I have an example here for a contractor who's involved in repair jobs. What you see in the table is how many days it takes him to complete a job and how many jobs fell into each of those categories. If I already have the data summarized in this way, I can use the weighted mean to calculate the average number of days it takes him to complete a repair project. The X bar again represents a mean. The little W down here is for weighted mean. The little W here is our weight, so it's the weight for the individual value. The X is our data value. So we multiply the weight by the data value, and then we add them all up. We divide by the sum of the weights. So we had a weight of 4 for the first data value 5. So we do 4 times 5 plus 12 times 6 plus 8 times 7 and so on. On the bottom, we add up the weights or the frequencies. 4 plus 12 plus 8 plus 2. Simplify the top, simplify the bottom, and then divide. And we see that the average length of time it takes him to complete a project is 6.31 days. Another example of a weighted mean is what's my grade going into the final. So for this example, I've used the distribution of the grades from our syllabus. All the little formative assignments that you do add up to be 30% of your grade. We've got a unit exam for each of the 4 units in the class. Those each count as 10% of your grade. And then your final exam will count for 30%. Suppose that these grades in the table represent your grades for the course. We're getting ready to take the final. You're curious about what your grade is in the course. You want to be able to calculate that on your own. So I've taken each weight and put it next to its grade. So 30% times 95, 10% times 75, and so on. The denominator is the weights for each of the grades I've included in the numerator. So I punch this into my calculator, 30% times 95, and so on. Got this 60.4 on the top. The bottom is 30% plus 10 plus 10 plus 10. We get down to 70% on the bottom. Your course grade at this time, given this distribution, is 86.2%. There are other measures of location that we might want to calculate. Percentile and quartile. When you think about percentile, you might think about things like the standardized tests that you took in school, where you might have gotten in the 93rd percentile. So what does that mean? Well, the percentile is the percent of data in a sorted data array, percent of data that are less than or equal to that value. So if you were the 93rd percentile on that standardized test, it means that 93% of the people who took that test scored less than or equal to whatever score you got. That also means that 7% of the people who took that test got greater than or equal to the score that you got on the test. Quartiles are a similar kind of thing. Quartiles really just divide the data up into fourths. So the first quartile is really the 25th percentile. The second quartile is the 50th percentile, which also happens to be the median. It's the value that stands right in the middle. The third quartile is the 75th percentile. Okay, so how are we going to calculate percentile? We're going to sort the data in order from lowest to highest. We're going to calculate this percentile location index, which is really just taking the percentile. So if it was the 93rd percentile, we'd put 93 on the top here, times the number of data points. If our percentile location index is not an integer, we're going to round to the next highest integer. The number in that location will be our pth percentile. If I is an integer, then we're going to average the ith and the ith plus 1 value together, and that average is going to be the pth percentile. So an example, let's find the 60th percentile in an ordered array of data. Here we've got 19 values in our ordered data array. I'm going to find the location index. So I plug 60 in for P. There are 19 data points, so I put that in where the N is. And when I simplify that, I get 11.4. So I round up to the 12th position. Now all I have to do is count down the data list until I get to the 12th position. We'll notice it's 82. 82 represents the 60th percentile. Here's a visual of quartile to help you think about this. To label the quartiles, I use Q1 for quartile 1, Q2 for quartile 2, and so on. Quartile 1 is going to be the data value that divides the data so that 25% of the data is to the left of that number and 75% of the data is to the right. The second quartile is also the median or the 50th percentile. 50% of the data would fall to the left, 50% would fall to the right. The third quartile would be the point in the data at which 75% of the data values are less than or equal to that, and 25% are greater than or equal to that. We'll come back to this later, but I wanted to note here that the interquartile range is the difference between Q3 and Q1. It's really actually how far it is from Q1 to Q3. It's this range of the center 50% of the data. An example of quartile. Find the first quartile in an ordered array of 19 values. We're going to use percentile location index that we did before. But what we're going to do here, we're going to replace the P with the percentile associated with the quartile that we're interested in. So in this example, since we're trying to get the 25th percentile, or first quartile, we're going to replace the P with 25. Simplify this, and we find out we should be looking at the 5th position. So we round up for this just like we did for percentile. Go down the data set till you find the data value in the 5th position. 51 would represent the first quartile for this data. 25% of the data values would be less than this, and 75% of the data values would be greater than this. A Box-and-Whisker plot is actually a way for us to graph the data and get a sense of the distribution of the data. It tells us some things similar to a histogram, but in a slightly different way. Notice that there's a central box here with the data and extended whiskers that come out here. So kind of think about this like the kitten's nose and the whiskers, Box-and-Whisker plot. And then if there are data values that fall outside these limits, which I'll show you how to calculate in a moment, those data values are considered way far away. They're outliers in the data. So how do we build a Box-and-Whisker plot? In class, we're actually going to do this in Minitab, but you should have a sense of what's happening here behind the scenes. So the first thing you do is find the first quartile and draw that in. Draw the median in also on the number line, and the third quartile, and close that in with a box. And so we get the rectangle. Then you calculate the lower limits. So we find this interquartile range, Q3 minus Q1, and multiply it by 1.5. Then we subtract that from the first quartile. So see, it says Q1 minus this 1.5 times the interquartile range to get this lower limit. We do the same thing with the upper limit. We take Q3 and we add 1.5 times the interquartile range, and we get that upper boundary. If there are data values that are outside those calculated limits, we put a little star to indicate there's additional data points out beyond the limit. It's also important to note that we can draw these horizontally or vertically. Now we can use the box plot or Box-and-Whisker plot to talk about symmetry. You notice that when the data look left skewed, the box plot is going to have a long left tail, a long left box. So the left half of this Box-and-Whisker plot is long and spread out. This means the data points over here are spread out farther apart from each other, and the data here are tightly packed together. If the data is symmetric, then it's going to look like a beautifully symmetric Box-and-Whisker plot. When the data is right skewed, we're going to have lots of spread in the right half of the picture. So the right box and the right tail will be long and spread out, and the left half of the data are compact and smushed together. So long right tail, right skewed, long left tail, left skewed, just like we saw before. An example of a Box-and-Whisker plot. So I've used a simple set of data here. We've drawn in the first quartile at 2, the second quartile at 3, the third quartile at 6, and created a rectangle around that. Then we've calculated the lower limit. Well, actually the lower limit went out beyond 0, but we can't go below 0, so we've put the bar at 0. When we calculated the upper boundary, we took 6 minus 2 to get 4. That's the interquartile range. Multiplied that by 1.5 to get 6. 6 plus 6 would get us 12. This 6 here is this 6. So 6 plus 6 gets us 12, and 12 is our upper limit. Notice we do have one data value out beyond 12. That's the number 27. Since it's way beyond that 12, we put a little asterisk out there, and this tells us that this data is right skewed. Long right box, long right tail, and a data point way out here, so we know that the data are right skewed.